Math 1108, Section 8.5, Division with Radicals and Rationalizing Denominators. The quotient property of radicals. Let n be a positive integer if the nth root of a and the nth root of b are real numbers, and b is not equal to 0, then the nth root of a divided by the nth root of b is equal to the nth root of a divided by b. We saw the quotient property of radicals in section 8.2, but the examples there worked out nicely because the radical and the denominator simplified to an expression without a radical. Here is an example of the ones that we saw in section 8.2. Simplify the radical expression. Well, we can write this as a quotient of radicals, the square root of 98x to the fifth in the numerator, and then in the denominator, the square root of 9y to the fourth. Notice that in the denominator, 9y to the fourth is a perfect square, so the square root of a perfect square is an expression without a radical, without a square root. The square root of 9 is 3, and the square root of y to the fourth is y to the second. In the numerator, there's a little bit more work to do. The largest factor of 98 that's a perfect square is 49. 49 times 2 is 98. And the largest factor of x to the fifth that's a perfect square is x to the fourth. X to the fourth times x is x to the fifth. So we'll rewrite the numerator as the square root of 49x to the fourth times the square root of 2x. And then when we simplify, the square root of 49x to the fourth is 7x to the second, which is multiplied by the square root of 2x. And then we're dividing by 3y to the second. Okay, that is an example of what we saw in section 8.2. In this section, it will be more complicated if after simplifying a quotient of radicals, there is still a radical in the denominator, then further simplifying is necessary. The completely simplified radical expression will not have a radical in the denominator. The process of eliminating a radical from a denominator is called rationalizing the denominator. So we'll do a number of examples from now until it's time to stop this video. But in each one, I'll explain the procedure. So we're going to simplify each quotient of radicals and rationalize the denominator. Okay, on this one, we have the square root of 7 divided by the square root of 3. The square root of 7 in the numerator is as simplified as it can be, and the square root of 3 in the denominator is as simplified as much as it can be. But we have to get rid of the square root of 3, or the square root, from the denominator. Okay, so the way that we do it, if we have a square root of some number in the denominator, we ask ourselves, when we look at the radicand 3, we ask, well, what would I have to multiply by 3 to get a perfect square? I would have to multiply 3 times 3, which is 9, to get a perfect square. So that tells us that we need to multiply this quotient of radicals by 1 in the form the square root of 3 divided by the square root of 3. We're just multiplying by 1, so we're not changing the value of this number. We're just changing its form. Okay, then we can multiply those two quotients. In the numerator, the square root of 7 times the square root of 3 is the square root of 21, because 7 times 3 is 21. In the denominator, the square root of 3 times the square root of 3 is the square root of 9, because 3 times 3 is 9. But we can simplify the square root of 9 in the denominator, And the simplified answer is the square root of 21 divided by 3. So now you see that the end result, the expression, does not have a radical in the denominator. So we say that we have succeeded in rationalizing the denominator. Okay, in the next example, this time we have the cubed root of 7 divided by the cubed root of 3. Okay, this one's a little more complicated than the previous example. Since the denominator has the cubed root of 3 in it, we focus on this radicand in the denominator, the 3. We ask, what would I have to multiply by 3 to get a perfect cube? Well, if I multiply 3 times 9, I get 27, and 27 is a perfect cube. So that tells us that we need to multiply by 1 in the form the cubed root of 9 divided by the cubed root of 9. All we are doing is multiplying by 1, and so we're not changing the value of the number. We're just changing its form. Okay, so in the numerator, the cubed root of 7 times the cubed root of 9 is the cubed root of 63, because 7 times 9 is 63. And then in the denominator, the cubed root of 3 times the cubed root of 9 is the cubed root of 27, because 3 times 9 is 27. But the numerator, or the denominator, will be simplified further, because the cubed root of 27 is 3. 27 is a perfect cube, and the cubed root of 27 is 3. So now we have a denominator that is a rational number. There's not a cubed root in the denominator anymore. Okay, so all of these examples have the same idea. We just have to analyze what we see in the denominator and then multiply by 1 in the appropriate form. So in this one, we have 6 divided by the cubed root of 25. So we need to ask this time, well, the radicand in the denominator is 25. What would I have to multiply by 25 to get a perfect cube? Note that 25 is 5 to the second, and we know that 5 to the third is a perfect cube. So if I multiply 25 times 5, I get 125, and 125 is a perfect cube. So this tells us, in effect, that we need to multiply by 1 in the form the cubed root of 5 divided by the cubed root of 5. We're just multiplying by 1, so we're not changing the value of the number. And in the numerator, we're just going to get 6 times the cubed root of 5. And in the denominator, the cubed root of 25 times the cubed root of 5 is the cubed root of 125, because 25 times 5 is 125. But now we can simplify the denominator. In the numerator, we still have 6 times the cubed root of 5. And in the denominator, the cubed root of 125 is 5. And we once again succeeded in rationalizing the denominator, which is to say that the denominator is a rational number. There's no longer a cubed root in the denominator. Okay, this next one, this time we have 7 divided by the 4th root of 9. Remember that 9 is 3 to the second power. So since it's the 4th root of 9, we ask, what would I have to multiply by 9 to get a perfect 4th power? If I multiply 9 times 9, I get 81, and that is a perfect 4th power, because 3 to the 4th is 81. And so we're going to multiply this by 1 in the form the 4th root of 9 divided by the 4th root of 9. Once again, we're just multiplying by 1, so we're not changing the value of a number. if we multiply it by 1. In the numerator, we're going to get 7 times the 4th root of 9. And in the denominator, we're going to get the 4th root of 81, because 9 times 9 is 81. And then the numerator is already as simplified as it can be, 7 times the 4th root of 9. And the denominator, the 4th root of 81, is 3, because 3 to the 4th power is 81. Now we have a rational number in the denominator. We succeeded in rationalizing the denominator. Okay, in the next example, the square root of 3 divided by 20x. Okay, well, there's more than one way to go about this one. I'll tell you what I recommend. Let's go ahead and write this applying the quotient property of radicals. Let's rewrite it as the square root of 3 divided by the square root of 20x. And then we ask, what would I have to multiply by 20x to get a perfect square? We can focus on the numerical coefficient first. If I multiply 20 times 5, I get 100, and 100 is a perfect square. And then if I multiply x by x, I get a perfect square, because x to the second is a perfect square. So this time we will multiply by 1 in the form the square root of 5x divided by the square root of 5x. And then we'll multiply the two radicals in the numerator. The square root of 3 times the square root of 5x is the square root of 15x, because 3 times 5x is 15x. And then in the denominator, the square root of 20x times the square root of 5x is the square root of 100x to the second, because 20x times 5x is 100x to the second. And then in the final step, we can write our simplified answer, the square root of 15x divided by 10x, because the square root of 100 is 10 and the square root of x squared is x. So we're assuming that x is a positive number so that we don't have to write the absolute value symbols around the x. Okay, on the next page, we'll work out some more examples. Okay, at the top we have the cubed root of 125 divided by the cubed root of 16y. Note that the cubed root of 125 in the numerator simplifies to 5, so let's go ahead and do that. And then in the denominator we have the cubed root of 16y. So now we ask, what would I have to multiply by 16 times y to get a perfect cube? Well, 16 is 4 to the second power, and we know that 4 to the third power is a perfect cube. In other words, 64 is a perfect cube. And we know that y to the third is a perfect cube. So this indicates that we should multiply by 1 in the form the cubed root of 4y to the second divided by the cubed root of 4y to the second. We're just multiplying by 1, and anytime you multiply a number or an expression by 1, you're not changing the value of that expression, you're just changing its form. Okay, so in the numerator, we multiply 5 times the cubed root of 4y to the second. And in the denominator, the cubed root of 16y times the cubed root of 4y to the second is the cubed root of 64y to the third. And then in the final step, the numerator is 5 times the cubed root of 4y to the second. And the denominator, the cubed root of 64 is 4, and the cubed root of y to the third is y. And that is our simplified result. There's no cubed root in the denominator, so we have succeeded in rationalizing the denominator.